Hello everyone, welcome to another Watch Me Do Math video. In this video I'm going to be talking about the question in the title. Are energy and momentum even real? Are they real things? I'm going to try and keep this video fairly brief and focused because it is a really fascinating concept, and it would be a shame if people clicked away because I was rambling more. So I actually have a semblance of a bullet-pointed script that I'm going to be using to direct myself through the video. So first I will basically explain what these two things, energy and momentum, are. They are two quantities which are conserved in a system as it sort of changes its state. And the fact that these quantities are conserved, or at least we have the theory that they are conserved, they remain constant, their total remains constant in an isolated system with no external forces. We have this theory about the fact that they are conserved, and it's never been proven wrong, which makes them an incredibly useful problem-solving tool. So basically, energy and momentum are these two conserved quantities that relate to the modeling of the way that different things in physics, different bodies interact by means of forces. It takes this idea of forces applied over distances and over times to create these two systems of mechanical thinking, firstly thinking in terms of work, energy, and power, or in terms of momentum, impulse, and force, which are both useful in solving physical problems. To put a little bit of math on the page, the sort of energy system is the system in which you're looking at this equation, essentially. If you are someone who takes IB Physics or GCSE Physics, this may be familiar to you. The work done on an object, the energy imparted to it by a force, is equal to the magnitude of the force applied to the object multiplied by the displacement through which that object was pushed. Okay? Whereas momentum, or in the impulse done, the momentum transferred to an object, it's sort of a parallel system of this mechanical thinking, where the impulse is sort of the change of momentum, which can also be written as the force applied to an object multiplied by the time for which that force was applied. And this may be a little different from the typical definition of momentum. The typical definition of momentous, impulse. The typical definition of impulse, J equals delta P, change in momentum, i.e. J is mv1 minus mv2 for a constant mass, or J is mv2 minus mv1, m delta v is ma delta t is f delta t. Hopefully I've explained as to why this could be considered the force times the time, even though it's usually delta p. That's a bit of an aside, because this formula for momentum, J is ft, holds true only when we're talking about a body of constant mass. So we will talk about a body of constant mass for this explanation, at least. So these are two parallel systems of mechanics, and the beautiful thing about these sort of parallel ways of looking at how motion and forces shape the behavior of physical objects around us is the fact that there's this idea called Noether's theorem, and I would be lying if I said I understood it well at all. I'd be lying if I said I even understood it superficially, but that's sort of a term which you can kick off from if you want to learn more about this idea that I'm going to talk about. So basically, this book I was reading, The Theory of Almost Everything by Dr. Robert Urter, it's this particle physics book which spends quite a lot of the second chapter out of 10 talking about this fairly abstract mathematical idea Cold-Noether's theorem. But the most important insight, for me at least, when reading the book, was the fact that this energy way of looking at things is sort of quote-unquote time invariant, according to that book. And this is something I was able to corroborate with some of the guidance or key ideas in the IB Physics syllabus. So this energy system of looking at things is quote-unquote time invariant, and this momentum system of looking at things is quote-unquote displacement invariant, or space, not displacement invariant, it's more like space invariant. And essentially the idea here is that if you have a system where time is not a factor you know a lot about, then work done, sort of energy transfer or work done, is a better way to approach that system, because work done is a time invariant concept. As long as it's the same force pushing the same thing through the same distance, then it doesn't matter the distribution of time over which that force pushed the thing, although it's not possible to really have distribution in this ideal case of constant force over a straight line displacement. This work done does not regard time as an element in the problem solving at all, which makes it useful. On the other hand, in problem solving with momentum, it is space invariant. So if we think of time invariant, we think of no matter when something happens, or at what speed something happens, the equations surrounding the transfer of energy in the system will remain the same. Energy will be conserved, the work done will be the same, so on and so forth, ideas like that. Whereas if a system is dealt with through the principle of conservation of momentum, this idea of momentum is space invariant. So because it's a force over a time, it doesn't matter if over what distribution of time the force was applied. Even if it's a really fast moving object and a force of 1 Newton was applied for 1 second, it would transfer the same amount of momentum no matter how the body was moving in the first place, right? So it doesn't matter what happens in terms of the body's position in space as it moves around and receives that force. The solutions to the problem will still be the same. So forgive me if this is not something that's quite easy to talk about, but I hope to give a more concrete example by looking at force distance graphs and force time graphs, because of course these formulas are for really idealized situations with constant force, which is obviously not always the case in real life. So suppose you have some force distance graph. The beautiful thing about the concept of work is that it doesn't matter sort of over what distance the force was applied, or what force was even applied. The important thing is that this W equals Fd could be shrunk down to deal with only a particular infinitesimally small distance, dd. Sort of like dy in dy by dx, or dx in dy by dx, or so on and so forth. It's an infinitesimally small quantity. If that force is applied over that distance, then it provides us with this infinitesimally small amount of work that's been done to the body in question. And if you were to integrate both sides, if you were to sum up every infinitesimally small bit of work that is done on the body, then you find this expression, the integral of force with respect to distance, or as you may geometrically interpret it, the area under the force distance graph. So the cool thing about this idea of work, of solving physics problems using the work energy power system, is that you're just looking at this integral of force with respect to distance, the area under the force distance curve. So it doesn't matter if the force distance curve looked like this, or like this, or like this. It really doesn't matter what line it is, as long as the area underneath the force distance curve is the same, or as long as the area underneath the force displacement curve, at least in one dimension, is the same, then it becomes like the solution to the problem will be the same, because the work energy power system of solving problems makes no distinction about this sort of the distribution of force over time. So for a really fast moving body, if you, like, I suppose the differing shapes of the graphs is not really the point here, but the fact that if you have a particular body which is going to experience a force distance graph that looks like that, it doesn't matter if the body's moving super slowly through this entire system. All that matters for the work done to be the same is that the body has this much force and this much displacement, making no assumption to the amount of time it takes for the body to move through it. It might be moving really fast and go through all this displacement really fast, but as long as the force on it follows this force displacement curve, the same amount of work will be done to a stationary body versus a really fast moving body. And similarly on the momentum side, as long as the area under the force time graph is the same momentum is transferred. If you have some force time graph which you know a body is going to go through, it doesn't matter where the body is. The body could be as long as this force is applied to the body at a particular time, the amount of impulse, the amount of momentum transferred to that body will be the same, because it's the area under the force time graph, taking there to be some dj, the infinitesimal amount of impulse, to be equal to the force times the infinitesimally small time over which that force was applied, integrating both sides to get j is integral of f with respect to time. So that's sort of the beauty of this whole system, that these are two parallel systems, and with three key things: 1, force; 2, distances, positions in space; and 3, positions in time. And each of these systems can ignore either the timing of events or the positioning of events and still get the right answer. And I think that's pretty damn amazing, man. Like, these guys must have been so insanely smart to come up with this stuff. Like, it's really freaking cool. So I've sort of explained the momentum and energy systems of problem solving, the way they work, the fact that each system of problem solving is so uniquely brilliant, and the fact that you can have this quantity that's conserved and use the fact that it's conserved to solve tons and tons of problems. But are these quantities real? Are they real? Are energy and momentum real? So that's the thing. These are theories of mechanics come up with by a few really freaking smart guys from Europe in, I don't know, the whatever century, 17th, 18th century, and I'm probably just going to talk at this point. So you can move to another tab if you like, because this is more of a philosophical topic than a physics topic. You have these guys coming up with this theory that's incredibly good. To this day, has never been shown not to be obeyed in some form. Like, if you have a theory that stands the test of time so well, then surely it's going to become such an incredible problem-solving tool for literally everyone who has even the slightest use for it. Because if these two things have never been shown to be disproven, which is really the only way that science can move forward, is to try and disprove things, right? If these things we've been trying to disprove them for hundreds of years and we've never seen them being violated, at least to the best of my knowledge, then there's one argument that because these theories are so good, they must contain some fundamental truth about the universe, and therefore the quantities of energy and momentum are real. But on the other hand, people also argue that energy and momentum are not real. They are just problem-solving systems that help us make sense of the mathematical abstraction that is a quote-unquote force. Like, you can't see a force, you can't, well, like, you can feel a force, but you're not really feeling something. It's just your brain processing inputs from the physical interactions around you. You're not necessarily feeling the force, you're feeling the effect of a force, or you're feeling the effect of some physical thing that's being modeled by the mathematical concept of a force, but you can't really observe or sense a force in the usual sense. So that's why some would argue that these two quantities, momentum and energy, are not real things. They are just mathematical tools which happen to be ridiculously, obscenely accurate at describing the universe. But going forward from both sides of this argument, so one side says it's so accurate, it must be true at some fundamental level. Another side says, yeah, but we can never know. We just know that they're really accurate mathematical models of the world. There's another crowd which is like, there's a phrase used by Jim Al-Khalili in his book Quantum, which is there is a shut up and calculate crowd. And this shut up and calculate crowd makes use of these two problem-solving systems. They do the physics, they make the predictions, and the predictions are really accurate. And the idea is you really shouldn't care, because this frame of view basically says, look, the science is so accurate. Modern science especially is so accurate. There's one quote in that book I mentioned earlier, The Theory of Almost Everything. It was some experimental prediction about a property of the electron that was accurate to like 1 part in 10 to the power of God knows what. And it is a quote from the author, it was the same accuracy and precision you would need if you were to shoot a soda can and hit it if you were firing a gun on the Earth and aiming at the soda can on the moon. It's something that's pretty mind-bogglingly crazy, and that's the interpretation taken by some of these people with regards to this question. So it's not that they're real or they're not real, it's that no one should care because they're just really effective at making predictions, and it's not the job of scientists to worry about whether things are real or not real. But that's like, part of me wants to say that's no fun. Isn't it interesting to wonder whether these things are actually real? But like they say, if it works, it works, and there are some reasons to believe that they contain some fundamental truths about the universe, and some reasons to doubt that any scientific model can ever be considered real. And now the third, not really third, but a fourth answer to this question, an alternate perspective put forward is that they are real, but they're only real because we're living in a simulation, and they are the manufactured product of something else. So they're real in the sense that Harry Potter is a real thing. Spells in Harry Potter are real phenomena insofar as you might exist in the Harry Potter world. Because the argument basically is, if it is possible, if there is a universe full stop, and it is possible to create simulations of a universe in that universe, then the probability that we are living in a simulation must therefore be very high, due to the fact that there's probably more than one simulated universe. So the odds that any given universe is the non-simulated one is pretty low. Like if there was one true universe and 100 simulated universes, then there'd be 101 universes in total, and the probability that we're in the real one is 1 in 101. That's one theory, and the idea that surrounds that theory is because the universe we are in may be a synthetic product of some other intelligent races or coincidental physical happenings ability to simulate the universe, we can logically conclude from that, or not really logically conclude from that, but the argument is, if it's a creation of someone else or something else or some other random accident, then it is real as far as a work of fiction is real. It is real as far as human creations are real, like maths, for instance, because it's just rules that the simulation runs on. It's like, if you play Monopoly, the rules of Monopoly are real things. It's information, basically. And the argument taken by this fourth group of people is that energy and momentum are real. These physical quantities, these mathematical models used to describe the universe are real because they're information, and information is real. Okay, so that like this video went on for longer than I'm expecting. I'm going to cut it off at this point because I'm just rambling. But hopefully, my presentation of these 4 perspectives in answering the question, are energy and momentum real, was quite interesting. And if you have any comments or questions, be sure to leave a comment or send me an email at watchmedomath@gmail.com. And until next video, thank you for watching. Bye-bye.